So in the previous lecture, we developed the basics of Borel measures on arbitrary spaces, measure spaces, and now we have to implement what we saw there on our sequence spaces. So in particular, what we have to do is find a nice simple algebra that generates the Borel sets on which we can specify measures in a nice and simple way. And we will see that this is indeed possible. In fact, it works out very nicely. So it's very easy to specify Borel measures on sequence spaces. So let's start with trying to develop an algebra that generates the Borel sigma algebra on our sequence space. So we will do the development for this simple alphabet, for the binary alphabet, but it works similarly for any other discrete alphabet. So we know the Borel sets are generated by the basic open cylinders, and therefore it suffices to find an algebra that contains all cylinder sets, because then this algebra generates the sigma algebra that the cylinder sets generate, so the Borel sets. Of course, assuming that every set in the algebra is also a Borel set. So recall that for an algebra we need two things. We need closure under finite unions, and we need closure under complements. Well, let's try to be as lazy as possible. So let's just see what we need starting out from a cylinder set in order to complement or to turn it into an algebra. So what sets do we need to add? So well, finite unions of cylinder sets are finite unions of cylinder sets. They're certainly not cylinders themselves, but only finite union of cylinders. But what about complements? What is the complement of a cylinder set? Well, let's look at this. So the complement of a cylinder set here is, again, a finite union of cylinder sets, namely the union of all cylinders generated by strings tau that are of the same length as sigma. Here's an illustration what the complement of a cylinder set looks like. So here we have our cylinder generated by a string sigma, so all infinite sequences extending sigma. So how can we describe all the sequences that are not in this cylinder here? Well, we take the length of sigma, right, this level here, and then we take all the cylinders that are generated by a string tau of the same length, but that is not identical to sigma. And now this observation is actually very nice for us, because, again, the complement of a cylinder set is a finite union of cylinders. So together with a closure under finite union, so a finite union of a finite union of cylinders is again a finite union of cylinders. So that means the set R, consisting of all finite unions of cylinders, is an algebra. So in order to specify a Borel measure on a to the n, it therefore suffices to specify an additive set function defined on finite union of cylinders. That means we have to just define a set function that is additive. Recall, that means that whenever we have a disjoint union of a set, then the measure of that union is the sum of the measures of the individual parts. And now we just have to apply this to finite union of cylinders. So here this requirement is written out. So if we have cylinders sigma 1 up to sigma n, pairwise disjoint, then we have to ensure that the measure of the union of the sigma I is the sum of the measures of the individual cylinders. So this is the function we have to specify. Well, how do we construct such a function? Well, let's start with the very basics. The minimal requirement, I mean, that's easy to see, is that the function mu, our measure, behaves as follows. The measure of a cylinder is the sum of the measures of its two possible extensions. Recall that we are working with a binary alphabet, so sigma will have just two possible extensions, sigma 0 and sigma 1, right? And the measures of those two cylinders here must give the measure of the cylinder sigma. But now it turns out that this is actually sufficient. That's the nice thing about measures on sequence spaces that I mentioned in the introduction. This condition, star, saying that the measure of sigma is just the measure of its two extensions for all sigma, is sufficient to specify a full Borel measure on sequence spaces. How do we see this? Well, assume that mu is defined for all cylinders and it satisfies this condition, star. Well, now we want to extend mu from just being defined on single cylinders to being defined on finite unions of cylinders. And to do that, we can proceed as follows. Well, we take a finite union of cylinders, and if they are pairwise disjoint, these cylinders, well, then we have no choice. We have to put the measure of the union this way, because that's just the condition for being an additive set function. But what if the sigma I, the individual cylinders, if they are not pairwise disjoint? Well, then we cannot use the definition above, since we would count some measure multiple times, right? There could be overlaps in the cylinder, and then we could count measure twice or even more times. So how do we get around this problem? Well, the solution is we use the very nice behavior of cylinders under intersections. Namely, we have the following observation. If I have two cylinders, sigma and tau, then exactly one of the following holds. Either they are disjoint, or sigma is contained in tau, or tau is contained in sigma. So it's not possible that they just overlap a little. Either they don't overlap at all, or one is contained in the other. And we can even say a little bit more. We can even relate this intersection behavior of cylinders to the compatibility or comparability of the generating strings. Namely, the two cylinders are disjoint if and only if the two strings are incompatible. Meaning that sigma and tau, neither of is an initial segment of the other. Now, two holds if and only if sigma actually extends tau. So we can also illustrate this here. So if sigma extends tau, so this would be sigma, and this would be tau, we see that the cylinder sigma is fully contained in the cylinder generated by tau. And likewise, for symmetrical reasons, the cylinder tau is contained in the cylinder generated by sigma if and only if tau actually extends sigma. This simple observation will be used in the following lemma. If we have a finite set of strings, sigma 1 up to sigma n, Then we can find another finite set of strings, sigma 1 star up to sigma m star, such that both sets generate the same open set, and the sigma star strings actually are pairwise disjoint. So the cylinders are pairwise disjoint. That means that by the previous observation, these here are pairwise incomparable. So again, the sigma j star induce the same open set as the sigma I, but as cylinder sets, they are pairwise disjoint. And again, by the observation we had that the disjointness of cylinders means that the generating strings are pairwise incomparable. It means that the sigma j star being disjoint, that no sigma j star is a prefix of another sigma star k. And this property is actually a fundamental and very important property for this course. And we give it a name. We call such a set of strings prefix-free. So again, prefix-free means no string is an initial segment of another string in this set. So here is an example of a prefix-free set of strings. None of the strings is an initial segment of another string, whereas here that set would not be prefix-free because this string here is a prefix of this string. How do we prove this lemma? Well, we just sketch it. It's actually not very hard. So, but I recommend you work out the details. I'll just go over the essential arguments here, steps. So first, we observe that non-empty intersections between sigma i's, cylinder sets, can only arise if one sigma I extends another. That's what we just observed. But if sigma I extends sigma j, then the cylinder sigma I does not contribute anything to the open set that is generated by the finite set of strings, because this is already covered by sigma j. So sigma j adds much more, potentially much more to the open set than sigma I. Hence we can obtain our prefix-free set sigmas of the sigma stars by successively deleting extensions till we remain with a prefix-free subset. Right? Because those things, those extensions, don't contribute anything to the open set. So how can we use the lemma now to assign a measure to an arbitrary finite union of cylinders? Well, we can do that as follows. We replace our original set of strings by a prefix-free set of strings sigma star sub I that generates the same open set. The lemma says we can do that. And then we just put, since now we have a pairwise disjoint sets, we just put the measure of our original union to be the sum of the measures of our sigma j stars, so the prefix-free sets. It's the same open set, but this is the measure now that we assign to the original union here. Well, this sounds all very nice, but isn't there a little problem? Well, what if there are many possible choices for the sigma 1 to sigma star? We haven't, the lemma doesn't say anything about uniqueness, right? And in fact, it's not unique. Is it true that we get the same measure independent of our choice of the sigma I star? And this is indeed the case. Namely, we have the following lemma. If we have two sets of strings, tau1 up to tau k and u1 up to ul. And if they're prefix free, and we also assume that they generate the same open sets, and we also assume that our function mu is defined on all strings, and it satisfies the property star, namely that the measure of the cylinder sigma is just the sum of the measure of its two extensions. Well, then one can show that the sum of the measures of the tau I is actually the same as the sum of the measure of the uj, meaning the measure is actually that we defined on the previous slide is independent of our choice of the prefix free set.